In the mysterious vastness of the Andromeda Galaxy, an amazing thing happened. A massive star, a beacon of light and energy, seemed to disappear, not with the expected blaze of a supernova, but in silence, fading into darkness. For as long as astronomers have studied the heavens, they've expected such stars to end in an explosive, brilliant death. But this star seemed to take a different route, bypassing the cosmic fireworks and plunging into darkness to form a black hole. This mysterious event has raised questions about how massive stars really die, and what causes some to simply collapse into darkness without the explosive finale. This is the story of that fading light, a case that challenges our understanding of massive stars and the mysterious processes behind stellar collapse. In the life of a star, balance is everything. Stars are locked in a constant tug-of-war between outward forces and inward pressures. At their cores, nuclear fusion reactions release colossal amounts of energy, pushing gas outwards and counteracting the star's intense gravity, which relentlessly pulls inwards. For stars with masses about 8 times that of our Sun or more, this balance holds for millions of years. But like all energy sources, stars eventually run out of fuel. Massive stars eventually exhaust their nuclear resources by fusing hydrogen into helium and onto heavier and heavier elements until they reach iron. At this stage, the star reaches a limit. Iron fusion does not release energy. It requires energy. This stops the outward pressure that once counteracted gravity, and the star's fate becomes inevitable. In most cases, this moment is a violent end. The star collapses rapidly under its own gravity, triggering an intense and explosive reaction. The shockwave from this collapse travels outwards, creating a brilliant supernova explosion. Supernovae are among the most powerful events in the universe, so bright that they can briefly outshine entire galaxies and illuminate the cosmos with their fading light for months or even years. The energy they release is staggering, and the aftermath leaves behind either a dense neutron star or a black hole, depending on the star's initial mass. This is how we thought massive stars ended their lives, in a burst of energy that ejected heavy elements into space, fueling the birth of new stars, planets, and even the building blocks of life. But in 2014 DS1, a massive supergiant star in Andromeda, has deviated from this path. Observations show that it reached the end of its life not with an explosion but with a quiet fade. Back in 2014, scientists noticed that the star was brightening in the mid-infrared part of the spectrum, a sign that it was in a late stage of nuclear burning, shedding its outer layers. For about 1,000 days, this brightening held steady, suggesting that it was nearing the end of its fuel reserves. But then something unusual happened. Between 2016 and 2019, the star's light faded dramatically, much more than expected. By 2023, despite the best efforts of astronomers and deep imaging techniques, the star was gone, leaving no optical or near-infrared trace. What had happened? Normally, such a massive star would end in a supernova, but the steady dimming of this star told a different story. It seemed that instead of going supernova, M31 2014 DS1 was experiencing what is known as a failed supernova. In this rare event, a massive star runs out of nuclear fuel, but instead of exploding, it collapses quietly into a black hole. The neutrino-driven shock that would normally reignite and explode the star's outer layer stalls, causing the entire core to collapse inwards, taking most of the star's mass with it. Failed supernovae are incredibly rare phenomena and present a fascinating puzzle to astronomers. So far, only a few candidates for failed supernovae have been identified, largely because they are characterized not by what they do, but by what they do not do. Unlike traditional supernovae, which burn brightly and can be seen across galaxies, failed supernovae fade quietly from view, their mass and light sucked into the core and condensed into a black hole. The absence of a visible explosion is their defining characteristic, making these events difficult to detect. The failed supernova of M31 2014 DS1 challenges our understanding of core collapse supernovae. In a typical core collapse supernova, the core of a massive star becomes so dense that the atoms within it break up, causing protons and electrons to combine into neutrons. This process, called neutronization, releases a burst of neutrinos, tiny particles that rarely interact with matter. However, at the extreme densities in the collapsing core of a star, enough neutrinos are produced to create a shock wave, which, in some cases, pushes outwards with enough force to eject the outer layers of the star and produce the supernova we can see. But sometimes this shock wave stalls. If it doesn't revive, the star's core will continue to collapse, and a black hole will form without the usual stellar explosion. In the case of M31-2014-DS1, the neutrino shock wasn't revived. The researchers observed that only a small amount of material was ejected, not nearly enough to account for a full supernova explosion. Nearly 98% of the star's initial mass, about 6.5 solar masses, was absorbed into the core, forming a dense black hole and leaving no luminous signature of its final act. The few traces left suggest that the star ejected a thin shell of dust, probably in its final moments of nuclear burning, but this shell quickly faded away, leaving nothing visible in the optical or infrared spectrum. The quiet collapse of this star adds to the small but growing list of observed failed supernovae. Back in 2009, astronomers discovered another potential failed supernova in a galaxy called NGC 6946, also known as the Fireworks Galaxy, because of its high rate of supernova activity. This star, designated N6946-BH1, was a red supergiant with about 25 solar masses. After a brief spike in brightness, it too faded from view, leaving only a faint infrared glow, a similar hallmark of a failed supernova. Observations like these suggest that failed supernovae may not be as rare as once thought. They could account for as much as 20 to 30% of all massive stellar deaths, suggesting that many black holes in the universe may have formed without a visible supernova event. These quiet, failed supernovae reveal an unexplored side of stellar evolution, where even stars that meet all the conditions for a supernova can instead quietly collapse into black holes. But what determines whether a massive star will explode in a supernova or collapse quietly? Astronomers are still trying to answer this question, but the answer may lie in the intricate processes that take place in the star's core. The final moments of a massive star's life involve the fusion of increasingly heavy elements until iron dominates the core. Once iron is formed, fusion cannot continue because it takes more energy to fuse iron than it gives off. This means that the outward pressure of fusion stops and the core collapses under gravity. The core collapse leads to incredibly high temperatures and pressures, triggering a process called photodisintegration, in which high-energy photons break up atomic nuclei. Neutrinos, a byproduct of these reactions, are produced in huge numbers. In some stars, these neutrinos deposit enough energy to create a shock wave that can blow the star apart. But this shock wave doesn't always manage to break free. Sometimes factors such as the star's mass, rotation, and internal structure determine whether the shock wave can overcome the star's gravity. In the case of M31-2014-DS1, these factors appear to have been aligned in such a way that the shock wave stalled, allowing the core to collapse completely without an outward explosion. The phenomenon of failed supernovae is teaching us that there may be more black holes in the universe than previously thought. If a significant portion of massive stars end their lives this way, then many black holes may have formed in quiet collapses, unnoticed by astronomers until now. This insight also suggests that supernovae may be only part of the story when it comes to the universe's heavy elements. If failed supernovae are common, then some stars may leave behind less in terms of dispersed elements, potentially affecting the chemical evolution of galaxies. M31-2014-D. S1's story invites us to consider that the universe may be full of quiet deaths and hidden processes that we are only beginning to understand. As we continue to explore the cosmos and refine our methods, we may discover even more cases of failed supernovae, revealing the silent formation of black holes that has been ongoing for billions of years. These findings challenge the simplicity of traditional models and remind us that even in the most extreme environments, the universe finds ways to surprise us. By continuing to observe and analyze stars like M31-2014-DS1, scientists hope to unlock the mysteries behind why some massive stars explode while others slip quietly into oblivion.